to minimize the release and retention of the particles or contaminants. Listed on the screen are 4 points of kind of the fundamental rules of clean rooms. So these contaminants, they can come from any source of particles. If you're looking at outdoor air, it's going to have pollen into it. We're going to have dust particles and vehicles exhaust. When you're looking internally into the clean room, you're going to look at people for the most common source, as well as the processes and equipment that are in the room. The amount of particles in the clean room, we control them through airflow, filtration, and room or area pressurization. And we will dive a bit more into that after we look at some industry applications. So what type of industry applications are we seeing in North America? A large opportunity that we see right here now and in the coming years are these two microelectronics manufacturing sectors. This would be EV battery or semiconductor manufacturing. They're getting a ton of investment and a lot of rapid growth in North America. And there's a ton of onboarding of offshore manufacturing is being brought into North America now by some of the top companies. If you're looking at the EV battery plant, Tesla, BMW, Ford, GM, all the major players are starting to make them here in North America. Now, if we look at another kind of two applications that we commonly see, some that have been around for multiples of years, and they're continuing to grow, as most hospitals will have any one form of these, or laboratories and compounding pharmacies. So you'll see these at various places, universities, hospitals all over the place. They are here now and they are continuing to grow. With these four kind of applications, there's a ton of market out there for you guys to get into and continue to grow your business. Now I'll pass it over to Jack for standards and requirements.
Thank you, Dirk. So the main standard that is going to be governing cleanroom design in North America is the ISO 14644. So how ISO lays out these cleanrooms is to generate 9 different ISO classes. ISO 1 is going to be the most clean with the most strict requirements, and ISO 9 is going to be the least clean with the least strict requirements. So what these ISO classes state is that within the clean room, you need to meet certain particle counts per cubic meter of air. So for ISO 1, we're allowed to have 10 particles that are 0.1 microns or smaller, and 2 particles that are 0.2 microns or smaller, and no other particles within the space. And then if we get to ISO 9, we can see that the particle counts are much higher, and they're not even counting those smaller particles that we do in the more strict ISO classes. USP, which we'll get into in a little more detail in a few slides, is what governs compounding pharmacies, and it builds off of ISO 14644, but it introduces pressure relationships into the design requirements. And finally, the Fed standard 209E has been replaced by ISO 14644, but it's still common industry jargon. So you might be working on a clean room with a contractor that has a lot of experience in the industry, and you might hear them talking about a class 1 or a class 10 clean room that actually might not be an ISO class. They might be referring to that Fed standard. Now, what that Fed standard was doing was it was also relating the classes to particle counts, but it was particles of 5 microns or larger per cubic foot. So they're not directly comparable to the ISO classes, but as you can see on this table, a class 1 in the Fed standard would be roughly equivalent to an ISO class 3 in the current ISO 14644. Now, what the ISO class doesn't say is how to achieve those standards. They just tell you how clean it has to be. So luckily, there's been a number of studies done in this industry, and they've determined different ways to achieve those particle counts. So one that we often look at is this one here, done back in 2003, where they determined average airflow, air changes per hour, and ceiling coverage that is required to meet the standards laid out by the ISO classes. Now, a few things that I'll point out on this graph. When it says average airflow velocity, what it's averaging is the airflow velocity of the entire ceiling, not of the diffuser face. And so with these filtered diffusers that we're going to talk about, they're going to max out at roughly 100 feet per minute. And so when we're looking at a requirement of an average airflow velocity of 100 feet per minute, that correlates to a ceiling coverage of 100%, because that's how these diffusers are going to be operating within the space. And finally, we have the air changes per hour that is increasing as we increase the required cleanliness of the space. Now, ISO is also going to talk about where the diffusers and returns should be located within the space. So the most common application that we see is ceiling-mounted diffusers and low wall-mounted return grills. Now, this is because the airflow that's being provided to these spaces is going to be washing particles away from our critical areas, and we want to then exhaust those particles and airflow from the space as soon as possible. But for ISO 6 and less strict, we don't have to be as concerned about the diffuser placement within our clean rooms because we don't have to provide fully unidirectional airflow. For ISO 5 and cleaner spaces, we do have to provide fully unidirectional airflow. Now, what that means is we can still provide ceiling-mounted supply diffusers, but then we're going to need a floor-mounted or a suspended floor return system so that we're not forcing our air to change directions to be returned or exhausted throughout the space. Another application that is less common is a ceiling or a wall-mounted supply and a wall-mounted return. Now, with all of these applications, no matter if you're having specific requirements on diffuser placement or not, what you're going to want to do is place your supply diffusers as close to your critical areas as possible. This is going to flood your critical area with HEPA filtered particle-free air, and you're going to want to place your returns or exhausts as close to particle generating parts of your process as possible, so that you're encouraging those particles to leave the space as quickly as possible, and you're not encouraging the particles to travel towards your critical area. Now for the USP standard. So like I said, the USP standards are governing compounding pharmacies, and they are built off of ISO 14644, but they take it a few steps farther by talking about pressure relationships that must be maintained throughout the space. Now, USP 800 is dealing with hazardous compounds in these compounding pharmacies. And in these areas, the primary concern is actually staff or public exposure to hazardous compounds that might have negative impacts on their health. So in these types of locations, the hazardous areas, we want to ensure that our critical areas are negatively pressurized in relation to our other areas, so that any types of contaminants that get out of their container are not spread out throughout the space. This is in contrast to a more typical cleanroom design where we're concerned about what we're manufacturing and having contaminants get to that, which might be detrimental. And in these spaces, we want a positive pressure relationship so that we're not encouraging particles to get to our critical areas. We're forcing them away from our critical areas. So this is where USP differs from ISO 14644, but it will likely tell you that certain areas should be an ISO 5 or an ISO 8, for example, and then it will take it a few steps farther with the pressure relationships that are required. And now I will pass it to Dirk to discuss how we achieve these various standards through filtration.
All right, thank you, Jack. So when we're looking at kind of filtration, we're going to be looking at really, really small particles. It's kind of dictated through the ISO standards that Jack went through. So when we're looking at the different sizes of the particles, you can see some on screen. Up 1 micron particle is small and it can affect a circuit board, while the smallest particle that a human eye can see is around 25 microns, which is right around the kind of bottom size of a human hair. So now that we kind of have an understanding of the particle sizes, how do we actually remove these varying sizes of particles out of the air? This is done kind of through 4 filtration mechanisms. Before we dive into the mechanisms, we should kind of understand a little bit more of the HEPA and the ULPA media and how they're made. So most HEPAs and ULPAs are made from some sort of microglass media. These small microglass fibers, they're all bound together with various binders. And these particles all kind of put together, dried out in a thin form, kind of create a tight labyrinth or maze for this air to move through as it passes through this media. So the air slows down, it wraps around all these fibers as it passes through the media, and the small particles in the air are removed when they come in contact with any of the filter fibers that are in the media. And that is the basis of kind of how the filters work. And the four mechanisms that are going to be working during this as the air passes over top are as follows. The first one will be inertial impaction. So this is happens to the larger particles, 10 microns and above. So as the air is flowing in and around all these fibers, these are larger, heavier particles. So rather than traveling with the airstream, the inertial kind of heaviness of the weight kind of impacts them into the fibers, and they're kind of trapped by the fiber in that fashion. The next one will be interception. These are a little bit smaller in size, but about 1 micrometer or larger. And basically this one is just carried in within 1 radius of the filter fiber. So as it tightly wraps around and the air moves in and out of all these openings and around the fibers, as long as it's carried within 1 radius, it causes a collision and it becomes trapped. The next two, and we'll start off with diffusion. So this is really small particles, typically 0.1 microns and under. This happens during the random motion of the very small particles that cause a collision with the fibers. So this is the Brownian motion, which is the gas fibers. Basically, the really, really small particles are floating through the air, but they're not floating in the airstream. They're reacting in a crazy pattern that moves back and forth and eventually causes a collision with one of the fibers. And the final one, this one typically isn't on HEPAs and ULPAs, but it is something that we need to talk about, is electrostatic. This occurs when particles are attracted to the fibers by electrostatic adhesion. So these four mechanisms are going to give you your efficiency rating of your HEPA filters. And the percent efficiency is a function of the ratio of the upstream particle concentration compared to the downstream concentration that pass through the filter. This kind of is defined through the testing standards, which we'll go over to a little bit later. But right now we'll take a look at the most penetrating particle size. So filters are at their weakest at the intersection of the two principles, which are diffusion and interception. So on the graph, you can see the MPPS just above 0.1 microns. Any particle, whether smaller or larger, is going to be filtered better. So as we're going to the smaller particles, the filter is going to be capturing these through diffusion. And then as we get onto the larger particle sizes, these are going to be caught through inception and inertial impaction. And so the percent efficiency that you're getting on your HEPA and ULPA filters, as long as they're tested in accordance with one of the standards, which we'll talk to, will always give you your minimum efficiency, and all particles will be trapped better, whether smaller or larger particles. And one thing to note is that the filters are tested in accordance with the standards. They're tested at an airflow, and airflow will cause the MPPS and the efficiency to change. Most manufacturers recommend to keep your airflow within 20% of the tested volume to ensure that you're getting the tested parameters met. So in North America, when we're looking at our standards, there's kind of 3 standards that we see typically in North America. IAST, which is a North American standard, Institute of Environmental Science and Technology. There's various standards that get into the HEPA filters, CC001, CC002, 007, 21, and 34 as well. In Europe, EN 1822 is very strong. We will see that in North America from time to time, especially when some of the manufacturers are selling into the European market. Another one to discuss is the iOS standard. It's an international standard. It's very, very close to the EN 1822 standard, and looking to amalgamate the two in the near future so that there is kind of one international standard for everybody to go to. But typically in North America, we're seeing right now is IAST be the major player, with EN 1822 kind of coming in the near second place. So when and where do we use these filters? We're looking at MER filters or ASHRAE filters as pre-filters to preserve the life of HEPAs and ULPAs. The more pre-filtration you do, the longer your HEPAs and ULPAs are going to last, and the lower cost you're going to have at replacing them, as typically the MER or ASHRAE filters are a little bit lower cost, don't have as kind of good gel seal or gasket seal that the HEPA and ULPA filters do. By far, the largest one that we see used mostly is HEPA filters. They're all over the place in any clean room applications. And the only time we really see ULPA is in the most stringent ISO classes. So if you're in a large microelectronics manufacturing, ISO classes 6 through 8, you're probably going to see HEPA filters. And then once you get down into your low ISO classes, ISOs 1 through 3, maybe even 4, you'll start to see ULPA filters being used. We talked a bit briefly about the microglass media and the HEPA filters. We are starting to see some new synthetic media options coming to the market. This has been changing over the years. There was some problems with PAO loading. That seems to have gone the way of the wind. But this is an ever-emerging market, a new market, and I really want you guys to do your research before using, just to make sure that you're using it for the right application. It is a little bit different than our standard HEPA microglass media. So with that, I'll pass it on to Jack to kind of discuss the terminal equipment that's going to house all these HEPA filters.
Thank you, Dirk. So when we're talking about filters, unless you work in a clean room or an operating room, the most common filters, or the filters you'd probably be aware of, are these MERV filters that we've mentioned before. So these MERV filters are used as a pre-filter for these HEPAs to prolong the life of the HEPA filter. But they have a few significant differences. So if you've by chance changed a furnace filter before in your house, you've probably seen a MERV filter. Now these MERV filters have cardboard frames, and they simply slot into an opening between your ductwork and your furnace. So for these applications, that's completely acceptable, but your airflow is always going to take the path of least resistance. So in a furnace, there's going to be some amount of air that is going to go around the filter, and that's called bypass air. Now, for these applications where we have very specific particle counts to maintain, bypass air would not be acceptable. So the way that we prevent this and eliminate it with HEPA filters is by providing gel seal. Now, what a gel seal is first of all, the HEPA filters are mounted within an aluminum frame rather than a cardboard frame. And then in a moat around the aluminum frame, we have a trough where a gel is placed, and this integrates with a knife edge that is on the inside of your diffusers. This knife edge penetrates the gel and ensures that you have an airtight seal, eliminating bypass and ensuring all air goes through your HEPA filter. Now, part of the reason that we are so concerned about this bypass air, that we had to go to this length of a gel seal, is because it takes a lot more pressure to get air through a HEPA filter than it does through a MERV. So that airflow would be more likely to go around the filter than through it. The final thing to consider when thinking about HEPA or filtration is how do we utilize the filtration in the space? Obviously, if we place these filters around the room, they wouldn't be doing anything. We have to force air through them. And that's where our terminal equipment comes into play. Now, the most entry-level option that you'd look at for housing some sort of HEPA or ULPA filter in a clean room would be a laminar flow diffuser. Effectively, this is a device that connects to ductwork, houses the HEPA filter with that knife edge, and forces all air through the HEPA filter. Now, the cons of a system like this is that you're going to need a very large air handler in order to force the amounts of air required at the static pressure required for these clean rooms. You're also going to need large ducting diameters or duct cross sections because, again, we're forcing lots of air at high pressurization. And if we're doing a larger clean room with hundreds of diffusers, we would not be able to take advantage of a negatively pressurized common plenum, or negatively pressurized interstitial space, which we'll touch on in more detail in a few slides. Now, this is where something like a fan filter unit comes into play. Fan filter units are very popular for clean rooms, and they are effectively laminar flow diffusers with built-in static pressure generators in the form of a motor blower assembly. Now, the purpose of these fan filter units is to overcome the static pressure required by the HEPA filter on a case-by-case basis rather than relying on a large air handler system. Now, what this allows us to do is use smaller air handlers or rooftop units, reduce the size of the ducting, use these for recirculation, and utilize the negative pressure interstitial space that I mentioned before. And these are very popular on new construction where they're trying to utilize an air handler that may not have been designed for HEPA filtration. They're also very popular for renovation, and they're also very popular for new construction as well. Now, the pros of a fan filter unit is they're very efficient. Again, you can reduce that air handler or rooftop unit, reduce the ducting that's being used to supply these. Effectively, you can design your air handler to only cover your latent sensible heating and cooling loads and your fresh air requirements. And then the fan filter unit does all of the required recirculation in that space to get you up to your required air changes per hour. With these fan filter units and the laminar flow diffusers, you can have the room side filter replacement, which can be very beneficial. It's the quickest way to change filters in this market. And finally, you can provide individual control and control side balancing. Now, what I mean by control side balancing is typically with these diffusers, you would need someone to physically modulate a damper in order to balance the units. But because all of our flow is going through that motor blower assembly, we can actually balance these units via the controller. Now, this controller can be mounted on the back of the fan filter unit, like we can see in this image, or you could have arrays of fan filter units controlled by something like a building automation system, and then you can have someone balance all of your fan filter units from one convenient location. The cons with these systems is that you're going to have individual install, and you're going to have more components and more component connections. The newest and final system that we're seeing in this industry is common plenum fan-powered systems. Now, this is effectively multiple fan filter units connected with a common plenum with a much larger motor and fan wheel in order to provide the airflow, but have less components in the space. So the pros of these types of systems is that they can be cost-effective, and again, you have less components, which would reduce your install time, because these are typically installed in blocks, and we can see one block of these systems in the image on the left. The cons of these systems is because the entire plenum is going to be positively pressurized, there is a chance of leakage between your diffusers in that common plenum array. More coordination is required to incorporate the trades and fit these within your system. Multiple unique module designs are required, in contrast to doing a large fan filter unit array where you'd likely have the exact same unit repeated throughout the space. Each module would require that manual balancing, and retrofit and expansion opportunities face some complications with these systems. So now that we know a little bit about the types of equipment that are used in these spaces, how do we actually lay out that equipment in the space for an effective cleanroom? The first type of layout is called open bay design. Now, this is the simplest type of layout, and effectively, we're going to have one cleanroom, and that entire cleanroom is going to be the same ISO class. We're going to do this by evenly spacing our terminal end filter devices throughout the space, so that we're providing that HEPA or that the required airflow for that entire space. Now, the benefit of a system like this is that you can easily change the direction or change the areas in which processes are being completed within the space, optimizing your manufacturing line. However, the downside of a system like this is within a cleanroom, you're likely going to have a few different required ISO classes. You might require ISO 8 in certain areas, ISO 5 in other areas, and ISO 3 in other areas as well. Now, the downside of an open bay design is you're going to have to provide air to the most stringent ISO class of the entire space. So you're likely going to need more diffusers and more airflow that's not going to be fully utilized by those less restrictive ISO areas within the same cleanroom. And that's where a layered approach comes in. Now, in a layered approach, you're either providing physical or non-physical barriers, and you're separating your different ISO classes so that you're only providing the required airflow of each specific ISO class. The benefit of this is that you can reduce the equipment that's required in the space, which lowers the startup cost, and you can reduce the airflow that's required in the spaces, which reduces the operating cost of these spaces. Now, how this might look is something like this image we're looking at now. So in this area, the only part of the cleanroom that it requires ISO 5 is within the laminar airflow workbenches. Now, within those benches, they're going to have increased airflow in comparison to the room that they're situated in. That's what we call the buffer area. Now, that buffer area is only requiring ISO 7, so we don't have to have as much equipment and as much airflow as if we had just designed the entire area as an ISO 5. And finally, the ante-room only requires ISO 8, so it requires even less equipment and airflow than the buffer area. Now, the big benefits to a system like this is knowing what the processes are of your design. So in an ante-room, we're commonly going to see staff that are gowning up and washing up to enter those cleaner environments within your space. What that means is we're going to be generating a lot of particles in the ante-room. So even though we're generating a lot of particles, this isn't a critical step in our manufacturing procedure. So we're not as concerned about the particles in this space, but we can easily exhaust them before they get to our buffer area or our workbenches, meaning that those particles are never going to come in contact with any critical parts of our procedure. Another design or typical layout that we see is called sectioned, also called modular or tunnel design. Now, the interesting thing with these designs is that they're typically sold as a all-in-one package, including your physical barriers, your supply diffusers, and potentially even a raised floor for return. Now, the big benefits of these types of systems is that you can easily utilize a space that wasn't designed as a clean room by buying these as a package and installing them in a space that maybe wasn't being fully utilized before, and now you have a clean space to do different types of manufacturing procedures that require that. The other big benefit of these systems is that they're modular and they're easily expandable. So if you decide to use a part of a warehouse that doesn't have full utilization right now for a clean room procedure and it's going really well, you can easily expand that clean room procedure by getting another section or module of these systems and connecting them together. And then that brings us to compounding pharmacies. Now, compounding pharmacies are an area where you're going to be creating a medication that either isn't available in that dosage or in that concentration or in that specific recipe. So these are targeted medications for people with specialized diseases and stuff like that. Now, like we mentioned before, there are kind of two main types of compounding pharmacies when it comes to the airflow design, which is hazardous and non-hazardous. So in those hazardous spaces, we're going to have a negative pressure relationship in our critical areas compared to their buffer areas. So this is a more complicated version of a layered clean room design. In our non-hazardous compounding pharmacies, we're going to have a positive pressure relationship between our critical areas and our buffer areas. So again, this is in the negative pressurization zones to prevent exposure to staff, and in the positive non-hazardous areas to prevent contaminants from getting to the medication, which might have negative effects on the end user. We also have sterile and non-sterile, and you can have a sterile hazardous or non-hazardous and a non-sterile hazardous and non-hazardous, and these are going to have increased air change requirements for those sterile areas to have lower particle counts within those areas. Now, how compounding pharmacies typically look at airflow is that they're going to have cascading pressure relationships. So just like that layered approach, we're going to have different ISO classes, but we're also going to have different pressurizations. And how they're going to do that is through the use of containment primary engineering controls, or CPECs, which effectively are going to be those flow hoods that we saw in the layered design previously. And we're going to locate those primary engineering controls within buffer areas, which are going to be our secondary engineering controls, or our CSECs. So they have some kind of big, long-winded explanations for these areas, but effectively, this is a layered clean room where you're paying a little bit closer attention to the pressure relationships between your spaces to further control the flow of contaminants within that space. Now, within all of these spaces, you have a few different options about how you're going to get air from your rooftop unit to your terminal devices. Now, a very popular use case in these clean rooms is to have unducted systems. Now, we touched on this a little bit previously, but a very popular use case is the negative pressure interstitial space. So this is going to be that your air handler is supplying to an interstitial space, and you have something like fan filter units pulling from that space and supplying into your room. Now, the benefit of a negative pressure interstitial space is that you're not going to have any leakage from your interstitial space to your clean room. And that's really important because there's no way to maintain the cleanliness of that interstitial space and keep it up to those clean room standards. So we need to prevent leaks happening in that direction. Another benefit is that your return system is going to work without the use of any fan powered device because you're going to be pulling back into that negatively pressurized interstitial space. Now, these can only be used with things like fan filter units. If we don't have fan filter units, we have to be using a positively pressurized interstitial space. And in this scenario, there is a potential for leaks from the interstitial to the clean room. So we have to ensure that we have an airtight sealing system so that we don't have those leaks traveling in that direction. Now, one thing to consider with these unducted systems is that you're going to have to pay a little bit more attention to the construction of the ceiling and interstitial space so that you don't have leakage. And even if you're not going to have leakage from your interstitial to your clean room, you might have leakage from outside to your interstitial space, which you want to prevent as well. So you have to pay a little bit more attention to the construction of the building. And if you don't have the availability to do that on a retrofit, for example, you might be more inclined to do a ducted system. Now, the ducted system also has multiple options. We can do direct ducted systems, mixing plenums, full recirc systems, the sky's the limit. And these are popular on systems where either we don't have control of the building or we get a little bit more temperature control out of the ducted systems. Or areas where we have less terminal devices. So obviously, as we increase the number of devices in the space, we're increasing the number of connections that would be required, and we see more benefits from those unducted systems. So in the industry, there's a few trends, future trends that we're seeing. So one of the things we're seeing is larger clean rooms. And what that means is more devices within the clean rooms. One way around that, and one of the things that the suppliers are now starting to offer, is the 4x4 fan filter unit. So previously, the largest fan filter units that were available would have been the 2x4s, and so the 4x4 effectively reduces the number of devices required by half. And so you're going to get roughly twice as much airflow out of a 4x4 as you would out of a 2x4, but it reduces the number of connections and motors and control connections as well. Another relatively new player in the market is integrated lighting. So this can be really popular for clean rooms that have high ceiling coverage requirements, because then you can still provide ceiling level lighting, even if you have 100% airflow or 100% ceiling coverage requirements in that space. So in that situation, you can still provide adequate lighting and the required airflow for whatever ISO class that you're looking at. And now I will pass it off to Dirk to go through our case study that looks at the energy efficiency of these units and how you can optimize a design by selecting different equipment within the space.
Thanks, Jack. So let's take a little look at the case study here. So for this case study, we're going to be looking at a clean room and basically comparing EC motors to PSC motors and doing a little bit of cost analysis on the energy savings that we can have. So this specific project, it was a 21,600 square foot ISO rated manufacturing clean room. It was in the state of California. It was built a few years back in March 2021. And the product or terminal units we were using were fan filter units. So the challenge that we faced was comparing upfront costs of the more expensive EC motor units with the operational costs of the whole system. So when looking at this, some of the key points that we needed to kind of take into consideration was obviously the rising energy costs. This was a few years back, but around approximately 18 cents per kilowatt hour at the time and location for the install. Some of the big things that we looked at for this project, which really helped us out, first and foremost was obviously switching from a PSC to an EC. So that's a big energy savings onto that one. But the nighttime setback opportunities also allowed us this. So we didn't just look at the operational costs of running 24/7, There was some applications in some of the less clean spaces or less higher ISO rated spaces that we could do some nighttime setback opportunities. So we adjusted the airflow in these opportunities, lowered it down, maintained the ISO cleanliness of the room because they were inoperational at that time. This allowed us to save a little bit more money. So in the end, when we're kind of looking at it all, the basis of design was an entry-level PSC offering. Again, we went to an energy-efficient solution with an EC motor option. Again, it was a 21,600 square foot clean room in the state of California, and it was fan filter units. And so we looked at two options with the customer. The energy-efficient solution one, which was just an EC motor with a forward curved wheel. But we also compared it to an energy-efficient option 2. Again, there was a little bit more upfront cost on this, but there was a continued annual savings on this as well, as the backwards curved wheel is a little bit more energy efficient than the forwards curved wheel as well. So in the end, the customer went with the energy-efficient solution 1, which was a 22% increase in the unit cost. But with all the energy savings we had on the nighttime setback and the energy savings from the EC motor, and the energy costs in the state, we were able to get a payback period of 0.96 months, or sorry, years, so less than a year. And year after year after that, there was a total savings of $279,000, which is a nice savings to pass on to any customers. It's also great for the energy and the environment. So with that, we'll be now entering the question period of our webinar, and I'll pass this part on to Julia.
Thank you so much, Dirk and Jack, and thank you to everyone who submitted questions throughout the webinar. If you would like to submit a question now, please